Everyone, today we're looking at this idea known as flux. And flux, by definition, is the amount of something passing through an area. That could be anything. It could be people passing through a doorway. It could be water flowing through a certain part of a pipe. But that's what we're talking about when we talk in terms of flux. We want to know how much of something is passing through different areas. And the something that we're going to deal with here is electric field. So how much electric field is going to pass through different areas. So when we define area, we have to define what we call length times width. And if you look at the board I have here, the length is the vertical height and the width is how wide the board is. But if you do length times width and you actually multiply them as vectors and do it as a cross product, areas are actually vectors. They point in particular directions. So for the board, the area points straight out. But for this flat piece you see here, the area points perpendicular to the surface. So you can see the electric field's in red there, and the area vector would be this blue arrow right here. The area would point away from the surface, 90 degrees from the surface, or it could point 90 degrees in the opposite direction, depending on which way you do your length times width. So any surface has an area vector, like the surface of the computer screen has an area vector that points either out towards you or in towards the screen. So using that idea, we can calculate flux by using the hoop. If we're trying to catch rain, you can see there's two orientations I can have for the hoop. I can have it parallel with the horizon, or I can have it perpendicular to the horizon. And which one will catch more rain? Well, the one that catches more rain is when you have the hoop horizontal. When you have the hoop horizontal, the area of that hoop is actually pointing upwards. So the area is pointing up or down, depending on which way you do your area. So that means that all the rain coming down would pass straight through the hoop. It would pass straight through that area and have maximum flux. And if you have that hoop at 90 degrees to the rain, if you have the area pointing left and right and the rain coming straight down, you get zero flux. None of the rain passes through that area. So there's three criteria to have the most flux possible for the rain and hoop example. The area, you can make the hoop bigger and have more flux. You could have it rain harder, so the amount of rain can tell you can have more or less flux. And also the angle between the hoop and we have the area vector pointing straight down. Let's say we have in our electric field. Our electric field is these solid red lines that are pointing straight down through our hoop. The angle between the hoop and the field, or the angle between the hoop and the rain, can determine how much flux we have. To determine flux, flux is the symbol phi, and you multiply the electric field strength by the area vector. But to get flux, it looks like the area and the electric field have to be in the same plane. That gives you maximum flux. And you get no flux when they are at 90 degrees to each other. So that means we have to multiply by a cosine. So that means flux is a dot product here of electric field dotted with the area, or E times A times the cosine of the angle between them. You get maximum flux when theta equals 0 or pi, minimum flux when you have your angle at 90 degrees or 270. So any perpendicular angle gives you no flux whatsoever. What are the units for flux? If we have a maximum flux, when you have the area and the field point in the same direction, remember, electric field is newtons per coulomb, and area is just square meters. So that's it. That's the mouthful for your units. It's Newton meter squared per coulomb for the amount of flux passing through a certain area. The note there says that flux for a closed surface could be positive or negative over the closed surface. It depends on how the lines are oriented and how they're pointing. So we made a couple shapes in class here. You can see these triangular pyramids or the cube. You can see that we have field lines pointing into the cube and coming back out of the cube. We had just a plate, and with the plate we just had field pointing through in one side and out the other side. And we had a little house shape the little house shape here, has field pointing in one direction and out in the other direction. So for all these shapes, we have field coming in through areas and out through other areas. So let's determine the net flux. If you see that I have this greenish blob around these two charges, you can see field lines that are passing out of the positive and they're going back in towards the negative. The total flux here, you can see, is all the outward lines are going to equal all my inward lines. If we want to do this mathematically, we could say that the area is pointing straight up and the field is pointing straight up. All these lines on this side gives me positive flux. And over on this side, my area is still pointing up, but now my field is going back in. So over here, all my lines represent negative flux. All the lines that are leaving give me positive flux. All the lines coming back in give me negative flux. So the total net flux of this system ends up being 0. Or of any of the shapes that we just made today in class, all the field lines passed in and out of your surface, so there was no total flux. Yes, there may have been positive flux on one side and 0 on the other, but the net result was nothing. But what about this shape? The group that did the triangular pyramid came across some issues when they were trying to deal with flux. If we've got electric field coming in the back end there and going through this wedge, you can see that the electric field's coming out and the area is at an angle. So we want to figure out the total net flux here. All the electric field passing through that back area passes through the front area too. So let's calculate this and show what our net flux actually is. And you can see our equation up there for flux is that flux equals the integral of E dot dA. So electric field dotted with the area for whatever shape we're dealing with. So here's our cube. I've given some dimensions to the cube so we can figure out some angles and areas and things like that. Let's have our electric field pass just like it did in the picture. It's passing right through the back and through the front there. Okay, so here we go. We've got the electric field passing from the back end through the front, through that wedge-shaped area. If we look at the back, you've got a flat area and you've got electric field that is going straight through it, straight into that area in all sides. Let's give the electric field a strength. Let's say the electric field is uniform and is a strength of 10 newtons per coulomb. And you can see that back cube right here has an area of 3 by 3. So the net area of the back is 9 square meters. So the net flux through the back is going to be 10 times 9, or 90 newtons per coulomb meters squared. Electric flux through that area is 90 newton meters squared per coulomb. But now let's look at this slanted end. For the slanted end here, the electric field strength is still 10. But we've got an issue now. When we look at the area vector for that slanted end, the area is pointing off at an angle. So the electric field is not fully going through that area, or the area is not perfectly parallel with the electric field. So if I want to calculate the flux through the front, I'm going to do E dot A times the cosine of the angle between them. Electric field is still 10 newtons per coulomb, but now we've got an area of 5 by 3, or 150 square meters. But now I got to multiply by the angle that's in there. So if I turn this on its side, you know I've got a 3, 4, 5 triangle, which makes this angle down here your 36.8 degrees. And if I look at my area vector points away like this. Well, I don't need all the area. I just need the area that's going to point parallel with this electric field, as that electric field goes from the back end to the front end. So if I do some of my trigonometry here, I know that this angle is the same as the inside, 36 degrees. So the angle between my area and my electric field ends up being 53.2 degrees. If I put 53.2 degrees in for my theta, do the work, and you end up with 90 newtons per coulomb meters squared. So it's actually the same amount of flux. In this case, you have positive flux coming out of the highlighted area. and we had negative flux coming in that back end. So negative flux through the back, positive flux as those arrows leave, gives you a total net flux of 0. So since all the electric field that enters the surface leaves the surface, no matter what the angle, as long as they completely come in and out, you get a total net flux of 0. So we're going to use this idea of net flux to determine electric field strengths based on looking at different shapes and seeing if there is a net positive or negative flux.